Today we are looking at exponential and log functions some more, but not just base e. So we're looking at y equals a to the x, where a is a constant greater than 0. To start off, and we've done some problems like this, to find dy dx, we've used logarithmic differentiation in the past to figure this out. And we still can use that, but what we're going to do is do this in general and be able to use a formula instead of having to do logarithmic differentiation every time. So we can always fall back on that, but if you can remember this formula, it'll make things a little bit easier, a little bit less work for you. So let's go ahead and work this out like we would have in the past. Logarithmic differentiation, we're going to take the natural log of both sides. And the reason for that is to go ahead and be able to get that exponent out in front. With properties of logs, we can take that x and bring it out in front of the natural log. So we get natural log of y equals x times natural log of a. Once we've done that, we can go ahead and do the derivative of both sides. So derivative of natural log of y, we get 1 over y dy dx. Over here, in a lot of problems in the past where we did logarithmic differentiation, we had to use product rule because we have two things multiplied here. But in this case, natural log of a, remember a is a constant, so that means that natural log of a is also a constant. And if we have a constant times x, what's the derivative of that? Just the constant, right? If this was 3x, derivative of 3x is just 3. Well, natural log of a times x, derivative of that is just going to be natural log of a. Right? Don't need to use the product rule when that's just a constant. If we use the product rule, it would just cancel out anyway because the derivative of the constant is 0. Well, so that's all we get over here. And then our last step to get dy dx by itself, we have to multiply both sides by y. So what we end up with for dy dx is natural log of a times y. But we can replace y with what it's equal to. Remember, y is equal to a to the x. So we have natural log of a times a to the x. And that's our derivative. Instead of having to do this long process, if this is a constant raised to x, we can just use this shortcut. Right? Derivative of a to the x, as long as a is a constant greater than 0, is going to be, and I'm going to kind of switch these around, a to the x times natural log of a. So there's one kind of like this that we did before and had a rule for with e to the x. Remember, if we do derivative of e to the x, what do we get? Just e to the x. Well, let's use this rule because e is a constant. It's bigger than 0. If we use this rule, we'd get e to the x times natural log of e. But what's natural log of e? 1. Right? Log base e of e, that's just going to be 1. So really that kind of cancels out. So that's still holds true. Derivative of e to the x is e to the x. So this formula works for that as well, except that just kind of cancels out because it's 1 times e to the x. Now, like most cases, we're not just going to have x up here. A lot of times we're going to have something in terms of x. So here we have derivative in terms of x of a to the u, whereas u is in terms of x. In this case, we're going to get a to the u times natural log of a, but then we have to multiply by the derivative of that exponent in terms of x. Right? So it's just same thing, but using chain rule. So we get a to the u, natural log of the base, times the derivative of the exponent. So these are two formulas that are going to help you to remember this and be able to do these without having to do logarithmic differentiation, doing all of those steps.